Good morning, ma. In previous class, we have seen tetrahedral complex and square planar complex examples. Okay, I will just revise the two examples. After that, we will continue with magnetic properties once again. Those are Ni Cn4 minus 2 and Ni Cl4 minus 2. These two complexes yesterday we have seen. Okay. Now coming to this NiCN4 minus 2, this is hybridization, DsP2 hybridization. This is sp3 hybridization, structure square planar, this is tetrahedral. Next, in NiCN4 minus 2, nickel, it is showing plus 2, Ni plus 2. Ni plus 2 means 4s to 2 electrons are removed, 3d8. Okay, it has no unpaired electrons. It has no unpaired electrons. This one has 2 unpaired electrons. Next, if it has no unpaired electron, then it is diamagnetic in nature. If it has 2 unpaired electrons, it is paramagnetic in nature. Paramagnetic in nature. Next, Hund's rule. Okay, Hund's rule is violated. Hund's rule is forward. Like this, we can write two comparisons for NiCN4 minus 2 and NiCl4 minus 2. Okay, this diamagnetic nature of this complex and paramagnetic nature of this complex was correctly explained by valence bond theory. These are found by magnetic susceptibility experiments. This complex and this complex were undergone magnetic susceptibility value in that experiments. In that experiment, this one got 0 magnetic moment. This one got some 2.87 like the magnetic moment. By that, they found this is paramagnetic in nature and this is diamagnetic in nature. Okay, and valence bond theory also successfully explained this diamagnetic nature and paramagnetic nature. But the problem is why that pairing is taken place towards inner electrons. That one was not explained. Why in this complex only that pairing is taken place? Why in that complex pairing is not taken place? That one was not explained by valence bond theory. That one we will discuss in drawbacks of valence bond theory. Okay, just observe these two, all of you. Okay, ma. These two, just observe, all of you. NiCN4 minus 2 and NiCl4 minus 2, hybridization, structure, unpaired electrons, diamagnetic, paramagnetic, Hund's rule is violated, Hund's rule is followed. Okay, like first two examples, I gave some comparisons, na? Like that here also I gave these comparisons. After completion of this, we will keep the heading that is magnetic properties of coordination compounds. Under valence bond theory only, under valence bond theory only, magnetic properties of coordination compounds. Till now we have seen the structures of coordination compounds. Next is reading magnetic properties. These were explained by valence bond theory. This is also under valence bond theory only. Okay. Now according to this one, magnetic properties were successfully explained by valence bond theory. Correct? Okay. What is the thing? See, all of you. Titanium plus 3. Next. Vanadium plus 3. Next, chromium plus 3. Three complexes which contains central metal atom, titanium plus 3 ion, vanadium plus 3 ion, Cr plus 3 ion. Okay, ma? Titanium configuration is argon 4s2 scandium titanium 3d2. Titanium 22 atomic number. Okay. Configuration argon 4s2 3d2. Ti plus 3 means how many electrons must be removed? 3 electrons must be removed. 2 electrons from 4s and 1 electron from 3d. So titanium plus 3 configuration is argon 3d1. Argon 3d1. Next, vanadium plus 3. Vanadium configuration is scandium, titanium, vanadium. This is 23 ma. Then argon 4s2 3d3. 4s2 3d3. Now V plus 3 means 2 electrons from 4s and 1 electron from 3d are removed. Then it will be argon 3d2. Next, chromium plus 3. Chromium configuration is argon 4s2 3d4. Cr plus 3 means how many electrons must be removed? 2 electrons from 4s and 1 electron from 3d. Then it will be argon 3d3. Okay, I am going to rub these nodal atoms configurations now. Now, under magnetic properties of coordination compounds, first I took three ions. Those are Ti plus 3, V plus 3 and Cr plus 3. These 3 ions. Now 3d1. What is that 3d1? 3d contains 5d orbitals. It has 1 electron like this. 3d2. 1, 2, 3d3, 3 electrons like this. Okay, man. Now see, this type of ions which contains 3d1 configuration, 3d2 configuration, 3d3 configuration, they did not face any problems to be explained with magnetic properties under valence bond theory. Under valence bond theory, this type of configurations, what are those? 3d1, 3d2, 3d3. These configurations didn't face any problem. Why? See, 1 electron. If it undergoes magnetic susceptibility experiments, okay, this one has 1 unpaired electron and these two are available with 4s0, 4p0. These two are available with 4s0, 4p0. It will be D2sp3. Even here also, these two are available with 4s0, 4p0. Again, we will get D2sp3. Again, here also, D2sp3. No need to take pairing of electrons, no need to violate Ohm's rule. That type of things are not required for this type of ions. Which are those ions? 3D1 configuration ion, 3D2 configuration ion, and 3D3 configuration ion. One more time, 3D1, 3D2, 3D3. Okay, if these ions undergo magnetic susceptibility experiments, after completion of the experiment, this one will be getting 1 unpaired electron, this one will be getting 2 unpaired electrons, this one will be getting 3 unpaired electrons. No problem. Okay, in every ion, these two inner orbitals are available. These two inner orbitals are available with 4s0 and 4p0. Okay, that's why there is no problem for D1, D2, D3 configurations. But the problem will be started for 3D4 configuration. Observe. Cr plus 2 or Mn plus 3. Cr plus 2 or Mn plus 3. Argon 3D4. If you want, check that one. Cr plus 2, Mn plus 3. Both have same configuration. Argon 3D4. Okay. Chromium 4s2, 3D4. Cr plus 2 means 2 electrons must be removed. When 2 electrons are removed, we will get 3D4 configuration. Same Mn plus 3 also. Okay, na? So it has 3D4 configuration. Now 3D4 means 5 d orbitals we have. 5 d orbitals we have. 4 unpaired electrons. 1, 2, 3. Up to 3, okay. If you write fourth one here, 2 d orbitals are not available from inside. See ma, D2sp3 configuration is undergone by, hybridization is undergone by 2 d orbitals from inside or 2 d orbitals from outside. It is not possible with 1 d orbital inside and 1 d orbital outside and sp3 like that. It is not possible. Okay, it is possible with inner 2 d orbitals or outer 2 d orbitals. There is no chance of one inner d orbital 3d, next s0, p0, 3 orbitals, and one again 4d orbital like that. It is not possible. Are you clear, ma? Now see, we have fourth electron. If you write fourth electron here, suppose if you write fourth electron here, we are not contained by 2 orbitals availability. Then what it will do? It will take help from outside. Four S0, 4p0, 4d0. Then it will take help from sp3d2 outside. Suppose if this electron pairs with inner electron, if it electron pairs, like valence bond theory, one complex is explained by pairing, one complex is left with pairing, correct or not? Okay, if this electron is paired here, then these two orbitals are available, then it will use D2sp3. Observe all of you now. Observe the first 3 complexes, all of you. First complex, titanium plus 3, has 3d1 configuration. V plus 3 has 3d2. Cr plus 3, 3d3. For these 3 complexes, we are not facing any problem because that outside 2 orbitals are, the 2 orbitals are there now, 3d last 2 orbitals. They are available for hybridization with 1 s orbital and 3p orbitals. Then it will be undergone D2sp3. There is no problem for them. But if you take Cr plus 2 or Mn plus 3 configuration, then it will be getting argon 3d4 configuration. 3d4 means there is a chance of 4 unpaired electrons by following Hund's rule. If that fourth electron is paired with first electron, okay, then another possibility we are getting. One more time I will repeat for Cr plus 2r, Mn plus 3. Let us see. These three I am going to rub these three more, okay. Write this one. Cr plus 2r, Mn plus 3. Configuration is argon 3d4, okay. One, two, three, fourth electron is paired here. Then it will undergo which hybridization? D2 sp3 hybridization. This one will be sp3 D2 hybridization. Okay, this is inner orbital complex. This is outer orbital complex. This one will be getting paramagnetic with 2 unpaired electrons. This is paramagnetic with 4 unpaired electrons. This 3d4 configuration, we face two types of magnetic properties. One more time. Two types of magnetic properties are shown by 3d4 configuration. This complex in some ligands, with some ligands, it will show inner orbital complex. Yesterday we have shown cobalt complex. In previous class we have seen cobalt complex. In one complex, that cobalt is felt with ligands NH3. In another complex, cobalt is felt with chlorine ligands. Okay, with NH3 ligand, it will form one type of orbital complex. Means with NH3 means it will form inner orbital complex. Correct. With Cl6, it will form outer orbital complex. Like this difficulty we will face with 3d4. 3d1, 3d2, 3d3, we don't face any problem. Are you able to understand, man? Okay, and one more thing. Both are paramagnetic only, but the difference is that both magnetic moment value will be same, different. This is paramagnetic, this is also paramagnetic. But here how many unpaired electrons are there? 2 unpaired electrons are there. Here we have 4 unpaired electrons. This is inner orbital complex, this is outer orbital complex. Correct or not? This is the problem we are facing with 3d4, 3d5, 3d6 configurations. Even with 3d6 also. Okay, that examples we will see, and all these are successfully explained by valence bond theory. But why this pairing is taking place? See here, instead of keeping this fourth electron here, I wrote pairing here. That is Hund's rule is violated. Here Hund's rule is violated. Here Hund's rule is followed. Why this Hund's rule is violated and why this Hund's rule is followed, that clarity was not given by, that is called qualitative interpretation of magnetic data. Simply, this is paramagnetic with 2 unpaired electrons. This is paramagnetic with 4 unpaired electrons. That information was given, and this pairing also taken place. These all explanations were given by valence bond theory. But why this pairing is taking place in some particular complexes only, with same Cr plus 2 or Mn plus 3. Here also same Cr plus 2 or Mn plus 3. That pairing is depending on ligands. Actually, that pairing is depending on ligands, not on the metal complex. See, Cr plus 2, Mn plus 3. Here also Cr plus 2, Mn plus 3. But here I wrote 4 electrons straightly like this by following Hund's rule, forming outer orbital complex. Okay ma. Here I just, instead of writing one electron here, I wrote here. Then we have shown D2sp3. That is the difference by getting 3D4, 3D5 configurations. Okay, that clarity by taking some examples, we will see that one. Let us see that. Before that, observe all of you what is present on the board. Okay, so on magnetic properties of coordination compounds, I took first three examples. Those are 3D1, 3D2, 3D3. We didn't face any problems with 3D1, 3D2, 3D3, but started with 3D4 onwards. In some complexes, 3D4 configuration is getting paired with inner electrons. In some complexes, that 4 electrons are not getting paired. Okay, because of that, outer orbital complex is formed. Previous condition, inner orbital complex is formed. Okay, because of inner orbital complex formation in Cr plus 2 or Mn plus 3, it will show paramagnetic nature with 2 unpaired electrons. Hund's rule is violated. As well as Cr plus 2 or Mn plus 3 in some complexes, it will show outer orbital complex with paramagnetic nature with 4 unpaired electrons. Okay, now let us take some examples now. By that you will be more clear about this magnetic properties of coordination compounds. Okay ma, let us see. Let us see the examples of these magnetic properties. First, MnCN6 minus 3 MnCl6 minus 3. These two complexes, let us see. In this complex, manganese oxidation number is plus 3. Observe, let it be X, cyanide minus 1, minus 6 is equal to minus 3, X is equal to plus 3. So Mn plus 3. Mn plus 3 configuration is argon, 4s2 3d5 is manganese. 3 electrons must be removed. So this is 3d4. Argon 3d4. Four is 0, 4b0. Now 3d4 in this complex, Mn plus 3 only. 1, 2, 3. Pairing will be taking place. Then 2 d orbitals and sp3. Hybridization is d2 sp3. Okay, now structure octahedral same only. Octahedral. Next, inner orbital complex. Inner orbital complex. Low spin complex. This is paramagnetic with how many electrons? Unpaired electrons, 2 unpaired electrons. Paramagnetic with 2 unpaired electrons. This is the information about MnCN6 minus 3. See, what is the oxidation number of manganese? Plus 3 in this complex. But pairing is taking place. 3d4 pairing is taking place. Instead of 1 electron here we got. Hund's rule is violated here. Now coming to the complex. In this complex, manganese, let it be X, minus 6 is equal to minus 3, X is equal to plus 3. So same configuration, Mn plus 3. configuration is argon 3d4, 4s0, 4p0, 4d0. But here pairing is not taken place. 1, 2, 3, 4, empty orbital. See, one orbital is only available. Two orbitals from inner orbitals are not available. That's why it will use outer orbitals only. That's why hybridization is sp3d2. Hybridization is sp3d2. Structure same, octahedral, outer orbital complex. This is using outer orbitals, no? That's why. Outer orbital complex. This is high spin. Why 4 unpaired electrons are there? No? That pairing is not decreased. Unpaired electrons are remain like that only. But pairing is taking place here. That's why low spin complex. Next, paramagnetic only with 4 unpaired electrons. Observe the two complexes now. MnCl6 minus 3, MnCl6 plus minus 3. In first complex, why that pairing is taking place? And in second complex, why that pairing is not taking place? The data was not given by valence bond theory, but it explained successfully. This first one is paramagnetic with 2 unpaired electrons, second one is paramagnetic with 4 unpaired electrons successfully. This was exactly coincided with practical results by magnetic susceptibility values. Okay. By magnetic susceptibility values also, we will get first complex 2 unpaired electrons, na? Second complex 4 unpaired electrons. That is explained, okay. But that pairing only, why it is like that, it was successfully explained by crystal field theory, not this valence bond theory. Okay. Next, I will take next two examples. Note down this clearly, man, all of you. FeCN6 minus 3 and FeF6 minus 3. Let the oxidation number of iron is x. X minus 6 is equal to minus 3, x is equal to plus 3. So we are going to write Fe plus 3 configuration. Fe plus 3 configuration is argon 3d5, argon 3d5, 4s0, 4p0, in this complex 1, 2, 3. Fourth and fifth electron are getting paired. In this complex, fourth and fifth electron should be written here, no? But Hundsman is not followed, no? It is violated. So fourth electron will be written here, fifth electron will be written here. Then 4 is 0 here, 4p0. It will use inner d orbitals only to undergo which hybridization? D2sp3. Now, what is the shape? Octahedral. Next, inner orbital complex. Next, low spin, this is paramagnetic nature with 1 unpaired electron. Paramagnetic nature with 1 unpaired electron. Next, here oxidation number of iron is same, x minus 6 is equal to minus 3, x is equal to plus 3, no? It is Fe plus 3. Fe plus 3 configuration, argon 3d5 same, but the thing is here, these 3d5 electrons are there, na? 1, 2, 3, 4, 5. These 4th and 5th electrons are not getting paired with another electrons. Okay, 4s0, 4p0, even 4d0, s0, p, d. Then it will use outer orbitals sp3, t2. Okay, here pairing is taking place, here pairing is not taking place. Same, octahedral outer orbital complex, high spin, paramagnetic nature, with 5 unpaired electrons. Paramagnetic nature with 5 unpaired electrons. This is about these two complexes, FeCN6 minus 3 and FeF6 minus 3. In both of them, the configuration is 3d5. Previously 3d4 we have seen, now 3d5. In one complex, pairing is taking place, in another complex, pairing is not taking place. According to that, this is the information, and according to that, this is the information. If it uses inner orbitals without 4d, then it is d to sp3. If it uses outer orbitals, then it is sp3d2, that is outer orbital complex high spin. This is inner orbital low spin, paramagnetic nature with 1 unpaired electron. This is with 5 unpaired electrons. This data also is exactly matched with magnetic susceptibility experiments. Okay, next one more comparison is there. That comparison we will see more. Just observe these two examples. See carefully, FeCN6 minus 3, FeF6 minus 3. In both the complexes, iron is getting plus 3 charge. But in first complex, pairing is taken place. In second complex, pairing is not taken place. Okay, the clarity you will get in crystal field theory. This is third time or fourth time I am telling for you. Please remember carefully. Very easy explanation. Okay, if you have more than one unpaired electron, if you have any one unpaired electron at least one unpaired electron, then it is paramagnetic only. But the difference we will get in magnetic moment values. First one is paramagnetic with 1 unpaired electron. Second one is paramagnetic with 5 unpaired electrons. Second one is contained by more magnetic moment value. First one is contained by less magnetic moment value. That is the difference. Both are paramagnetic only, but unpaired electrons are different, na? That is the thing. Okay, and we are going to take 2 more examples and we are going to compare them. Those are belonging to cobalt complex. Let us see them. Before that, I think you are very clear about this topic, ma? Next one, CO C2O4 thrice minus 3, COF6 minus 3, COC2O4 thrice minus 3 and COF6 minus 3. Okay, in this complex, oxidation number of cobalt is plus 3 because let it be X. C2O4 is minus 2 complex now. Charge present on C2O4 is minus 2. 3 into minus 2 minus 6 is equal to minus 3. X is equal to plus 3. Then it is CO plus 3 complex. Okay, CO plus 3 configuration. Argon 4s2 3d7 ma 2 electrons and 3d6. This is previously 3d5, this is 3d6. 3d6 means Hund's rule, if it is followed, 1, 2, 3, 4, 5, 6th electron must be coming here. But here 4th, 5th electron paired with this one and 6th electron is paired here. Okay, then 4s0, 4p0. It will use inner orbitals, only 2 orbitals are available, completely paired ma. Then this one will use D2sp3, then shape octahedral, inner orbital. Next, high low spin complex, diamagnetic in nature, octahedral, inner orbital, low spin, diamagnetic in nature. Why it is diamagnetic in nature? 6 electrons are getting paired with each other, na? So no unpaired electron is present. Okay, so if this complex is undergone magnetic susceptibility experiment, we got the resultant as it is diamagnetic with 0 unpaired electron. So it is proved. But why this pairing is taking place, why it is not following Hund's rule, that clarity is not there. Okay, now coming with this one, here also x minus 6 is equal to minus 3, x is equal to plus 3. So charge present on cobalt is plus 3 1. Then configuration, argon 3d6, 4s0, 4p0, 4d0. Then here Hund's rule is followed. 1, 2, 3, 4, 5, 6 as it is. Inner orbitals are not available to undergo hybridization. Then it will use sp3d2. sp3d2 hybridization means same octahedral only, but this is outer orbital complex, high spin, paramagnetic with 4 unpaired electrons. Paramagnetic with 4 unpaired electrons. Okay, this is exactly coincided with magnetic susceptibility values. This is about cobalt complexes, no? Observe these two. So everything I wrote with a D4 configuration 2 complexes. Okay, D5 configuration with 2 complexes and D6 configuration with 2 complexes. In D6 if electrons are paired, this is the condition. In D6 if electrons are not paired, this is the condition. So for everything I took one example with Hund's rule violated and Hund's rule followed. Okay, that clarification we will discuss drawback of valence bond theory and we will go for next theory, that is crystal field theory. Okay, no? This is about examples present in magnetic properties of coordination compounds. Okay, so in today's class we have seen all these things. Okay, in next class we will go through what are the drawbacks in valence bond theory. By this valence bond theory is completed. Okay, first we will see what are the drawbacks in valence bond theory in next class. After that, to explain the drawbacks of valence bond theory, next theory was proposed, that is called crystal field theory. Then what about that crystal field theory? We will start with next class. Okay, this is about today's class. I hope you are clear about this class, man. If you have any doubts, ask me, no problem. Okay, just once go through this too, all of you. Okay, ma'am. I hope you are clear about the concept what we have explained today. Okay. So with D4, D5 and D6 configurations, if electrons are getting paired and if electrons are not getting paired, according to that, how valence bond theory successfully explained the magnetic nature of these compounds. Okay. But the problem is here, why in particular compounds only that pairing is taken place? Why this in particular compounds that pairing is not taken place? That clarity we will get in next concept, that is crystal field theory. Okay, ma? That is about today's class. I hope you are clear. Okay, thank you all.